Good afternoon. We start this afternoon's program now. Like yesterday, the two talks this afternoon will be on protein folding and aggregation. Well, I should say like it was announced for yesterday, because Dave did sort of change part of his talk, talked about RNA experiments. But okay, so the first talk will be nucleation in protein folding. And Jayant, after the break, will talk to us about mechanisms of amyloid fibril formation. Jayant.
So, I understand that nearly all of you are physicists, and both talks today are really talks which describe the approach a chemist would take to study both folding and protein aggregation. And so I will allude to some computational work done by physicists. I will allude to some physical models, but the idea really is to present the other viewpoint to most of you, the viewpoint of those who do experiments on protein folding and protein aggregation, and what they think about processes happening to proteins as they either fold or undergo the other type of self-assembly, which is into aggregates. And I'll be talking about how they go into regular aggregates called amyloid fibrils. So before I start, I should warn you that I have some slides which are handwritten, and if you're right at the back of the room, you won't be able to read them. So unless you want to sleep throughout the talk, you might want to move in front. The first talk has only a few handwritten slides, but the second one has probably a dozen slides which are handwritten. So I'm going to be talking about nucleation in folding. And before I really start, I presume from Dave's talk yesterday and also talks in the previous week that you all by now know roughly that proteins are heteropolymers, that the polymeric chain is really a necklace of beads of 20 different colors, and each bead of each color is got a different type of chemistry. So some are nonpolar, some are charged positively, some are charged negatively, some are polar but don't really have a charge. And because of this, because proteins are heteropolymers, they have a chemistry of interaction which is very important in dictating how the structure is arrived at. And physical models of folding usually ignore the chemistry. The well-known funnel models, for example, really give no importance whatsoever to chemistry, and they ignore, they will only consider the protein as a chain whose energy barrier to folding arises completely from chain entropy and not from interactions within the chain which might be difficult to form. So if we now talk about a process such as this, which is going from a necklace of 20 different beads to a well-defined structure, so this is what you would call the unfolded state, and this is the folded state. Now, we know a lot about this state from crystallographic studies. There are tens of thousands of proteins whose structures are known right now. We know structures from NMR studies. Those are not perhaps as precise as crystal structures, but nevertheless, there are still several thousand NMR structures available. Unfortunately, we know very little about the unfolded state. The unfolded state has been called liquid-like. What that means is something which really reflects the point or the fact that one knows really very little about its structure. So it's been called liquid-like. There are lots of interactions present within the unfolded chain which are present in the folded chain. So you would have, except that the partners would be different. So you all probably know that proteins are stabilized by van der Waals interactions, hydrophobic interactions, electrostatic, hydrogen bonding, etc. interactions between aromatic side chains, etc. And many of those interactions could be expected to be present out here. And it's very difficult to get structural information on the unfolded state, because the methods of doing so are rather difficult to utilize. One can nowadays by NMR get some information about local structures in the unfolded state, but the experiments are pretty tedious to do and not very straightforward. And it's important to get some structural information on this, because if you, for example, know that there is some element of local fluctuating structure in the unfolded state, perhaps that structure might play a role in seeding the folding process. So it's become very important to look at the unfolded state. Now, if you look at the unfolded state, and now when we talk about unfolded state, I presume by now that many of you would be knowing that you unfold a protein by taking it into a high urea or high guanidine solution, or you take it to a high pH or to a high temperature. So if you unfold the protein chain, if you look at the distance distributions between points on the chain, especially, for example, if you look at the radius of gyration, or you look at end-to-end distances, these distances have distributions which are expected for a statistical random coil. So you would expect really there to be no specific structure in the unfolded state. But it's been shown by several groups that even if there are elements of structure in the unfolded chain, the distance distributions would perhaps still follow a Gaussian distribution characteristic of a statistical random coil. So it's not easy just by showing that you have a random coil distribution to say that there is no structure. You need to do the hard experiments to see whether there is structure, and typically you would do those experiments by NMR. And I will allude to one such study in the course of my talk. Now, so we want to know now, yes?
What kind of structures, if they are present, will also give a Gaussian distribution?
So what you can do, for example, and what has been done by George Rose's group, is just you take these elements of secondary structure, the helices and the strands, and in between out here, or even somewhere, even in the middle of these, if you now just randomize the phi psi angles, so you would essentially get small units of structure but otherwise randomized in arrangement with respect to each other. And then you look at, for example, the radius of gyration, you would still see a distribution, a Gaussian distribution. So it's not, you're essentially keeping nearly all the structure in the protein, but you will see these type of distributions. That's been done in one study so far. But so the question is, it's important to really know whether there is any local structure, and the question is, how does one go about trying to find out the local structure? So for example, it might be that the part of the chain which forms, say, this helix does form the helix in the unfolded state, or it might form this turnout here. Okay? So if it does, could these type of structures be dictating what happens next during the folding process? So the way you do folding experiments, at least, is to take a chain which is unfolded in a high concentration of urea or guanidine, and it's quite remarkable that you need molar concentrations of these chemicals to unfold micromolar concentrations of the protein. You start the folding experiment by taking this protein in high urea and just diluting out the urea. And the moment you dilute out the urea, the protein starts folding. The first step, which I talked about in my talk last week, is presumably the collapse of the chain, because you're going from a solvent in which what you would call a good solvent to a bad solvent. And so the chain collapses as expected for any polymer. Now the question then is, what role do any fluctuating structures in the unfolded state play in the collapse reaction as well as in any subsequent structure formation reaction? And okay, sorry, this time I have my own control. So we are now talking about a chain which is behaving like a random coil, and the question is, how does it start folding? So there could be fluctuating units of secondary structure, clusters of local structure which form first, and then these coalesce. Okay. Now there is a lot of poor usage of the term nuclei and nucleation in protein folding. Now, in strictly speaking, if one is talking about kinetic nucleation, so this is, for example, what you would talk about if you're talking about the crystallization of, say, polyethylene. The first step is rate limiting, and everything after that first step occurs quickly. Okay? So then you're talking about a small amount of structure which necessarily has to form, and which is, once it is sufficient for that to form, for the reaction then to proceed completely to the final state. And subsequent to the nucleus formation, in the case of crystallization of polyethylene, the reaction occurs very rapidly. The first step is rate limiting. Now, in the field of protein folding, because of the development of ideas in the field, and for example, the idea of fluctuating secondary structures or fluctuating hydrophobic clusters, the idea grew that perhaps these fluctuating structures are structures which act as nuclei, and they started being called nuclei in a very loose terminology. So the idea was that these are essentially initiation sites for folding. They're structural nuclei. They could also be perhaps called thermodynamic nuclei, in the sense that only a very, very small fraction of the molecules would possess these local structures, but they were not kinetic nuclei in the terms of what are involved in, say, crystallization of polyethylenes or other polymers. Okay. So,
Jan, sorry.
Yeah.
So you're saying that they're not thermodynamic nuclei in the sense of crystallization.
But they're not kinetic nuclei. So in terms of they're a structure which has to form,
right,
and its formation is rate limiting.
Right.
And everything subsequent is fast.
Right. Now this is what you're calling a kinetic nucleus.
Yeah.
Okay. But you said that it's not a thermodynamic nucleus.
I said you could call it a thermodynamic nucleus in the sense that it's a species which is populated to a very low extent because of its very low stability.
Okay. Yeah. No. So.
There is a lot of mixing of the terminology,
right,
and so a thermodynamic nucleus could be a structural nucleus,
right,
or it may not be a structural nucleus. Okay.
Right.
So there is some. So if you have, for example, helix coil theory of Zim and Bragg, the nuclei which they talk about in the theory is what I would call a thermodynamic nucleus, because it's the development of the theory is a thermodynamic development.
Mm-hmm.
It doesn't say anything about it being rate limiting in the actual process of helix formation, though it can be assumed to be the rate limiting step, because the probability of forming this thermodynamic nucleus is very, very low.
Right. Okay. So I guess, I just want to prompt you a little bit, because these are sort of subtle distinctions to make. So, I mean, one of the features of the thermodynamics of the system with which one associates nucleation is that the phase which the system is in at the initial state of a transformation process is locally thermodynamically stable.
Yes.
Right?
Yes.
Now, this will not be true under all circumstances. In other words, even if I can imagine that this phase can exist in metastable conditions. If I change the parameters of the environment, then for all parameters this statement will not apply.
Sure.
Right?
Yeah.
So, so the question is, the random coil that you start with, that's sort of the parent state, under folding conditions, can one legitimately think of as a locally stable or metastable state, or this is not possible? I mean, so it won't generally be true, but is it true close to the folding temperature or close to whatever is the threshold?
So there
condition?
is a lot of, I mean, I would say the answer is not really known, because what happens to this chain when you take it into refolding conditions is really something which is a matter of a lot of debate. And I tried to allude to some of those issues in the first talk. So you have a chain which is collapsing, which is contracting. The question is there some structures which have to come together in this collapse process? So in other words, you are then implying that the collapse process has some element of specificity in it. Do some elements have to come together in any particular molecule for that molecule to continue to fold? Okay? Or does it happen subsequently? So these are the type of issues I will try and discuss in this talk. Okay? So you have these type of either hydrophobic clusters or local fluctuating secondary structures which could come together, and then folding proceeds. Now, very early on, if I have, okay, so I'll come to that in a minute. There were ideas of nucleation which started coming into the field right from the time of Leventhal. Many of you would have heard of Leventhal as the originator of the Leventhal paradox, which was, why do proteins fold so fast when they have to perhaps sample so many different conformations? But he and then subsequently others brought out the idea of nucleation. And initially the idea of nucleation was that you had some element of local structure, and the stress is on local, which had to form for the rest of the protein to develop structure. So the idea here was really more of a structural nucleus. Okay? And we will come then to other ideas of nucleation as really propounded by Alan Furst, one of the leaders in the protein folding field. And I will give you my opinion of those ideas as we go along. So one of the things which we need to discuss about folding is really the question of an energy barrier. And this is because folding reactions have been treated as small molecule reactions. The idea was that you could project everything onto a single, the energy landscape onto a single reaction coordinate, and there's a lot of problems about what is the best reaction coordinate to describe the progress of the reaction. And if you had an energy diagram such as this, and if, for example, as this diagram implies, you have only U and N, and the two states can exchange with each other by hopping over an energy barrier, then this state at the top of the barrier would be the least populated state, the least stable state in the transition. So the idea would be that this would then be what you would call your kinetic nucleus. Your transition state, the transition state of small molecule chemistry, would be the nucleus for the folding reaction. So if you could characterize structure in this transition state, you had an idea of what was the nucleus for the folding reaction, because once this is formed, folding just proceeds downhill to the native state very rapidly. Okay? The time taken is really to hop to this state. So this was supposed to be the nucleus. Now, very early on in the earliest studies of protein folding in the 60s and, well, mainly in the 70s, folding reactions didn't seem to be describable as two-state, that you had only U and N. Intermediates were identified on folding pathways. And so the idea was that folding was not two-state but multi-state. And I'll come back to that a little later. But in the early 90s, mainly from Alan Fersh's work and from others' work, there seemed to be a whole set of proteins, mainly very small proteins. By very small, I mean 100 residues long or so, whose folding seemed to be describable as two-state. Now, the problem began at this stage because the moment you start calling folding two-state, the idea is that you cannot detect intermediates. It doesn't mean that intermediates are not present, and I'll come to that in a minute. But because the term two-state was used in a somewhat loose manner, the picture which people had was a picture like this. And then whatever structure was here was the structure of the nucleus. And we'll come to ideas which have come from this picture as we go along. Now, if you look at protein folding as a diffusive reaction, you have a chain, a polymer chain, which is diffusing from one state to the other, and it's going through many, many different states. Then you have small little motions in the unfolded state, and this is an enthalpy versus reaction coordinate plots, so you don't see a free energy barrier. The transition state then gets defined as a state, as an ensemble of structures, which you have to proceed through to reach the native state. Okay, that's more clearly depicted out here. If you say the red is the transition state ensemble, then when your individual protein chain could follow either this path, or if it starts out here, it could follow this path. To reach the native state, it has to go through a small fraction of the structures to reach the native state. Okay, so you had many, many unfolded structures, conformations, a few transition state conformations, and then fewer native state conformations. So the idea from this picture is really that because you are forced to go through the red, you're forced to go through a smaller set of conformations, you have an entropic barrier to the folding process. And the idea which came out from such studies is that the barrier to folding is really entropic in nature. So when I show a picture such as this, to a physicist, to many physicists, this barrier is an entropic barrier. But it's known now from studies with many different proteins that very often the barrier to this is of enthalpic origin. So for example, you might need some very specific interaction to form. Say for example, salt bridges. Salt bridges are what are electrostatic interactions which have a hydrogen bonding component, so that they have orientation is very important. So wherever you have orientation being important, you would have a barrier to that formation of that interaction. So you could have enthalpic barriers, or for the formation, for example, of a tripartite salt bridge, you might have a very strong entropic barrier to the formation of the interaction. Yes?
I didn't understand the transition state ensemble. I mean, is it the least number of states that has to be passed through? Because otherwise it's arbitrary, right? You could have a larger set anytime.
They are the conformations which you have to pass through. You cannot reach the native state without passing through one or the other member of this ensemble.
But is it the least number of them? Because ultimately even the whole set is, then you can call the whole set a transition state ensemble.
So what do you mean by least number? So we'll talk about structural aspects of that and what as we go along. I'll address your question a little later.
Okay. I guess, so one comment I have is I mean, without commenting on the nature of the transition state, whether that barrier, so I guess, the statement about entropic barriers would be, presumably if I'm going along the reaction coordinate, right, enthalpically it's a one-way street, presumably, right? So what seems to make sense to me as a statement is that the unfolded state has low free energy which arises from entropy. So
Yeah.
it doesn't really seem to make if you're only talking about the transition
No,
state,
so-
to say whether it's entropic or enthalpic is a little bit of a trick question.
So if one talks only about the chain entropy,
Right.
then you would get a different picture. What you also need to include is a solvent in the whole picture.
Fine.
And that contributes in a somewhat indeterminate way at present to the total entropy of the reaction.
Right. No. All I'm saying is that it's the unfolded state minimum which is entropic, rather than the transition state being an entropic or an enthalpic barrier.
What do you mean the unfolded state is entropic?
Meaning the unfolded state is stabilized, meaning acquires low free energy
Yes.
because of the entropy. And because in this picture, like what Ananya is asking, there isn't a very clear, so it's not the transition state here is not some well-defined narrow gate you have to pass through. It's just some point on the way. And the only uniqueness to that point could be that in your appropriate order parameter representation, if you're sitting at that state, you have a 50% chance of going to the folded state or not.
Yeah.
Right? So, so that would be my
Yes,
answer
I think
to your question.
I'll be talking about that as we go along.
Okay.
So I'll just.
Right.
So if you talk about going from an unfolded state to the native state, you're going from many different conformations down to the native conformation. So in this type of funnel picture, your unfolded states are at a state of high entropy. And you're going down, as you go down, the number of conformations is decreasing, so your entropy is decreasing, and your native state has got the lowest entropy. And if you have a kind of bottleneck out here, a kinetic bottleneck, that would really be a transition state, and we'll discuss this, as I said, as we go along. So the idea is that you have to go through a set of conformations to reach this native state. Now, so the question is, do all the conformations which are present as the bottleneck, do they possess some common structure or not? Okay? Or are they do they have completely different structures? So those are the type of questions one would be interested in. So, so as I said, the transition state picture comes from small molecule chemistry. So you have essentially a saddle point on your energy landscape. And so along the reaction coordinate, you're at the maximum, but at perpendicular, you're at a minimum. And the question is, what is the structure out here? Now, this type of picture which I've drawn out here shows an intermediate being present, and a stable intermediate, stable compared to the unfolded state. So if you have an intermediate which is stable with respect to this, what would you, in terms of a structural nucleus, you would say perhaps this transition state out here has a structural nucleus. Or there might be some structure which is formed right out here. Whereas in terms of a kinetic nucleus, this necessarily has to be the kinetic nucleus, because after this, the folding reaction has to be fast because it's downhill in free energy. Okay. So the problem of two-state folding becomes more complicated, because if, for example, as I said, the early studies from First and others suggested proteins really folded without any accumulated intermediates, but you cannot kinetically distinguish between a scenario such as this, where there's really no intermediate, and a scenario such as this where you have a high energy intermediate, because the kinetics are completely indistinguishable. In both cases, the rate is determined by the energy barrier from the transition state to the lowest state preceding the transition state, which is the denatured or the unfolded state. So this energy doesn't really come into the picture at all. So you cannot distinguish between this. So now if you start by assuming two state and you want to say this is the nucleus, you have a problem if the scenario is actually this. Because if it is this, then this might be the kinetic nucleus, but it may not be the nucleus from which folding proceeds. It may not be the structural nucleus. Okay. So this has been really the confusion in the field about what a nucleus in folding is and what role it might play in the folding reaction. And I'll try and give you an idea of how ideas have evolved in the folding field. So one point I also want to make about these barriers is that the barrier heights can be easily modulated or tuned by changing folding conditions. You could change temperature, you could mutate the sequence, you could do all sorts of things, and you can move the barrier along the reaction coordinate. You could remove the barrier completely by tuning conditions, etc. And then the question of even a kinetic nucleus becomes more hazy. Okay? You could, for example, change the structure, perhaps even change the structure which is present in the transition state completely by a change in folding conditions. So if you look at the more physical view of nucleation, you talk about a free energy barrier because, for example, when vapor becomes liquid, because you're talking about two phases, and these molecules come together, you have an energy term which goes as the volume of the collapsed molecules, and you have a surface energy term which goes as the square of the radius. So you have a term which goes as the radius cube and another term which goes as the radius square, and the two of them give you a barrier shape like this. Okay, I'll talk more about this in a minute. So you then end up having this free energy barrier because you have an R squared term for the surface energy and you have an R cubed term for the total internal energy of your nucleus, and so you have this energy barrier to the folding, to the say condensation of the vapor. Now if you try and look at a protein chain which is folding, the idea was that something similar to this is happening, that some residues, so the residues are shown as these circles, are coming together to form this nucleus, and you then have these loops which are coming from the nucleus which are adding to the entropy of the system. So this nucleus would be stabilized by enthalpic interactions within it, and it would be destabilized by entropic loop entropy. Okay. So you have this is 98 if I remember right, okay, in current opinion of structural biology. So so this is, you know, a picture which has been there for many years now. Okay, so let me go to an even earlier period. So one of the first ideas about nucleation came from Robert Baldwin at Stanford way back in 1972, and they were looking at the folding of ribonuclease A, a workhorse protein for experimentalists, and they suggested that the earliest step was a nucleation event, and they also suggested two different ways of thinking of why this first step is the rate limiting step. Okay, so for example, the idea was that you had in the unfolded state many different possible conformations of your including folded conformations. Okay, so to activate the polypeptide chain for rapid folding, a critical number of the regions have to simultaneously assume their correctly folded conformation. So in any one chain you would have perhaps one small bit of correct conformation, but you needed, for a chain to fold, it needed several of these small little bits of correct conformations all simultaneously on the same chain, and that was a very rare event. And because of that, the small equilibrium constant for nucleation results from the low probability of these different regions being in their folded conformations at the same time. Okay. And the other idea which they proposed is that nucleation is the attainment by random Brownian motions of the polypeptide chain of a condensed conformation that allows the chain to collapse into the native state. Now, the idea here is that even though the motions in the unfolded state are very, very rapid, the probability of having this very particular structure, the nucleus structure, was so low that the kinetics of its formation would be quite slow. Okay, and this was something which Flory had talked about in the 60s. Okay. Now, the free energy for nucleation came about because of the entropic cost of getting all the residues together in the right conformation in in the chains. Okay. So, so even the diffusion of the chain segments is very rapid, the appropriate three-dimensional conformation has a very low probability. So I won't really talk about helix coil transition. So I think I'll skip this, but or I'll just allude to it very briefly. I can leave my slides for whoever wants to look at them later. So I'll skip many of the contents of the slide. It's more to prompt me to say what I want to. So if you're talking about a helix forming, now for a helix to form, you have hydrogen bonds between residues I and I plus 4. So if you look at the geometry of a helix, the first two residues, the NHs don't form any hydrogen bonds because the residues preceding them are not in a helical conformation. So it's the CO of this which forms a hydrogen bond to an NH of I plus 4. So N residues are fixed by N minus 2 hydrogen bonds. Okay. Now the idea is this, that it is entropically very unfavorable to fix a helical turn. Okay, because you can fix one residue, the second residue, there's a big entropic cost, and the enthalpy, the favorable interaction which would favor this comes only after 4 residues have gotten into the right conformation. So there's already an entropic cost, and only after 4 residues are in the right phi psi angles will you have the hydrogen bond forming, which would stabilize this turn of the helix. So that's the idea of why, for example, helix nucleation is supposed to be a very rare event, or the equilibrium constant is very, very low. This is actually a treatment from Finkelstein in his book Protein Physics, and it really talks about an enthalpic component to this nucleation. And since anyway I think most of you can't read this, I'll skip this, and you can look at it on the slide. So let me go back to the early ideas about nucleation. So one of the first people who brought this to the fore was Wetlaufer, and much of the credit to nucleation ideas amongst experimentalists is attributed to Wetlaufer. And what he did was made contact maps for different proteins. So essentially you make a two-dimensional map where you put residue numbers versus residue numbers, and then you mark which residues are very near which residue by putting a dot there, so you know which residues come close to each other in the native state. And then you see whether there are small little contiguous segments of the chain which form a little contact in this contact map. So for example, if you have 6 to 8, or here they talked about 8 to 18 residues which are close together in the contact map, these, he suggested, could be nucleation sites for protein folding. And his idea was that these were structural nuclei, not really kinetic nuclei. Okay. There were other ideas at the time about nucleation. So it's known, for example, that in protein folding, at least for many proteins, a particular isomerization reaction of a particular residue proline can be very late limiting. And John Brands very early on suggested that this, so you have a particular bond which can be in a cis or trans isomer, and in the native state, if, for example, if the bond is always in a cis, then the unfolded state, the bond is trans. This trans to cis isomerization is very slow, and he suggested that's the first step. And because it's the slowest step, it would perhaps act as like a nucleation step. So these ideas of nucleation have got really nothing to do with the physical or the physics definition of nucleation, but it's the way chemists and biochemists have been thinking. Okay. The other interesting work from the 70s was really from Harold Sheraga's group, the work of Matheson, where they talk about a nucleus being the result of a very specific hydrophobic collapse. So this is an idea which later in the 80s and 90s, many of the physicists using lattice models have been propounding. But the ideas really came much earlier from Sheraga's lab, again by looking at structures of known proteins at that time. And so they looked for conformations whose existence can significantly increase the rate of formation of native structure, and suggested that it's a necessary but not sufficient condition for folding. So the nucleating site may form and not produce folding if additional cooperative interactions which follow it are prevented from forming. So if you, for example, don't change conditions for it to fold, the nucleus might be fluctuating in and out, but it doesn't cause structure to form. Okay? And they suggested that it might be a specific pocket stabilized by hydrophobic interactions. Yes?
While the formation of the helix, does all the substituents, point outwards, or some may be protruding inwards also, like small substituents like glycine or alanine if they are in the chain?
You mean to say the side chains?
Yeah, side chains.
The side chains are all outwards. You can't go inside.
Yeah, okay. And one more question, the environment inside, is it perfectly inert, or there may be some charges?
Inside
The helix.
There's no space for anything inside the helix.
Okay.
But the main chain is highly polar.
Polar, okay.
Okay, the main chain has got carbon and a CO and a NHCO.
Yeah.
And so that is extremely polar.
Mm-hmm.
Okay, so that, but there's nothing can be contained within the helix.
Okay.
It's just too small.
Not even ions?
No.
Okay, thank you.
Not in alpha helices. I mean, you could have other helical structures formed by proteins which can contain. Okay. So the way Matheson and Sharaga were thinking about nuclei, and this is from a more recent paper from Sharaga just a couple of years ago, was that these hydrophobic interactions perhaps bring specific residues together, and this might then act as a nucleus for further structure formation. Okay. So the question is then, as I've talked about right in the beginning, is there little pockets of structure, maybe hydrophobic structure, or structure stabilized by hydrophobic interactions, which is formed in the unfolded state itself. And to detect very small amounts of structure, when I say very small amounts of structure, I mean, first of all, in any one molecule, the structure would be fluctuating in and out. And if you look at a population of molecules, it will be present in only a very small fraction of the molecule. To detect such structures is very difficult. And there are now NMR methods developed in the last 5, 6, 8 years which can detect very small populations of molecules possessing some specific structure. And so I don't even remember this is a small little peptide it's a small, I think, designed protein, which this is the native state, so it's a very simple structure. In the unfolded state, it could be shown that some of the interactions which are present out here are also stabilizing a little pocket out here. You don't have the secondary structure, the helix being present, but you have these side chain interactions which are forming. And the idea was that this pre-existing hydrophobic collapse could be responsible for this protein to fold very, very rapidly. Okay. So you have many of these small proteins or proteins which fold very rapidly. And we'll come to what determines speed in folding. I'm way behind what else. Anyway, but if you look at very fast folding proteins, most of them have got quite a bit of helical content. And the idea, and this is an important point here, is that the idea is that because a helix can be nucleated at any point in the helix, you could presumably have many different pathways for folding, because in some molecules, and if you have many different, because nucleation, there are many different nucleation sites in the helix, and folding would be rapid because there are multiple pathways for folding. Okay. So let me now talk about very briefly about the early ideas about nuclei or nucleation, which came from lattice model, from simulations, computer simulations of folding. And so these experiments came out in the early, these computer experiments were done in the early 90s by several different groups, including Dave Thirumalai, who's away somewhere right now, and from Shaknowicz's group at Harvard. So what was done in these, I don't know much about how these simulations are done. They're lattice model simulations, and where you take a small little molecule on a lattice and make it fold into a predefined native structure. And what they determined in this very early study was that there was a particular nucleus, a particular structure which formed in all the molecules, and once that formed, folding proceeded rapidly. Okay? And so this is what they called a specific nucleus. And they also did simulations where they started with this preformed nucleus, and obviously if it were really a nucleus, folding should just zip along from it and without going back to the unfolded state. And that is what they observed, that formation of the nucleus guaranteed subsequent downhill folding. Okay. And Dave Thirumalai's group at about the same time looked at another lattice, off-lattice model, and this folded into some, this had three types of residues in it, not just polar, non-polar, and they also observed rapid formation of native hydrophobic contacts that is immediately followed by folding to the native state. Okay. And what interestingly they also observed was that not all molecules form this nucleus. So some molecules seem to be folding without going through this nucleus, whereas other molecules needed to have this nucleus to fold. I think that's shown in this picture from a recent review of Thirumalai, where he has some molecules going through an intermediate and then going to the native state, others undergoing a specific collapse and then going to the native state. And he also talked about multiple nuclei being formed during the folding process. So this is an idea which he and several others have propounded over the years. Okay. So in the specific nucleus picture, the transition state ensemble has a substantial entropy from the conformational freedom of the loops which surround this nucleus. If you recall the picture I showed you a short time ago. So the picture, so if for those of you who are interested in the kind of a survey of what has been done from simulation studies, this is a pretty recent 2009 review of computer simulation experiments on protein folding, on the nucleation mechanisms, on ideas about nucleation. So this is actually a picture taken from a paper by Tobin Sosnick, which is reproduced in this paper, and it brings to the fore about the various ideas about nuclei which have come about both from simulation work, which pertain to the question asked from behind there. So, do you have, in this structure, some residues which are absolutely required for folding forming structure, the dark ones, whereas others could be either completely unfolded if they're white, or if they are gray, they may or may not be involved in the in this transition state structure. Or you might have a structurally heterogeneous transition state, but in this heterogeneous transition state, there's always, in all the members of this transition state ensemble, you always have some residues involved in the same structure, whereas others may or may not be involved in structure. And or you might have a transition state which is completely different, that you could have in some members a particular nucleus, if you want to call it that, a structural nucleus, whereas others you have some other residues forming structure. So these are the various pictures which have come out from both experimental work and from various types of simulations. Now the problem for people like me who don't follow simulations too well is that a lot depends on what type of force fields you use and what type of interaction, essentially force fields you use for your simulation. So for example, these are for the same type of lattice, simulations done with different types of force fields, and you get very different nuclei structure in the three cases. Okay? So it's not easy to figure out what is correct from simulation work, and then as we'll come across very soon, it's not easy to figure out what is happening from experimental work either. Okay. So there have been other studies of nucleation using simulations from Shachnovich, who's been deeply interested in evolutionary aspects of folding. So you can look at, he could show that different sequences designed for the CI2 backbone, CI2 is a well-studied protein, have conserved residues at the predicted core or nucleus positions. And residues forming the nucleus are highly conserved in 23 natural sequences similar to that of CI2. So the advantage of doing, so the idea was this, that if you suspect that these residues A, B, and C are involved in the nucleus of a particular protein, then you would expect that for this type of structure, these residues are important. Then you could look at the family of sequences and structures, homologous or structurally similar to the protein in which you have identified this nucleus, and you could ask, are these residues conserved in evolution in all these family of protein, in all the members of this family of protein. So obviously you would expect that if a particular set of residues are acting as a nucleus and are hence presumably important in dictating folding, they should be conserved across members of the family. And what Shachnovich saw was that seemed to be the case for CI2, and I will be talking later about other studies which indicate folding nucleus residues are more significantly conserved than the rest of the residues. And actually, I think I will be, if I have time, I will be ending by showing experimental analysis which indicates that this result from simulations is perhaps not correct. So the other people who have been looking at transition states have been Vijay Pandey and Roksha, and they talk about transition state classes. So they essentially said small proteins have got unique transition states, whereas larger proteins would have either structurally heterogeneous or distinct transition states. It is again work coming out from simulations. Now I should mention, I am going to very briefly run through this paper by Vijay Pandey and Roksha. Vijay Pandey is well known now as the originator of the folding at home program, where he has many hundreds of thousands home computers doing folding simulations for him. But what I want to bring out here is that it's not easy. How do you define a transition state or what you'd call a nucleus in terms of a kinetic nucleus in a simulation? It's not at all straightforward to do. One way in which was a strategy suggested both by Shakhnovich and by Pandey Roksha was what Shrikant alluded to find out which is the earliest conformation at which you would have half a probability of going to the native state without going back to the unfolded state. So where your p fold, the probability of folding is half. Okay, but that was not a strategy used by many other people in the field. And the question really comes to what is the best reaction coordinate in simulation studies to describe the folding process. And there itself there is a lot of uncertainty about what reaction coordinate to use. Many of the simulation people use a quantity called Q, which I'll talk about very soon, which is the number of native contacts being formed as a sign of progress of the reaction. But that doesn't bring out the heterogeneity of the process, because you might have two conformations with the same number of native contacts, but there's no commonality at all between the structures of those. The number of contacts might be the same, but the structures might be completely different. So this is a simulation done by him using the Go model, where you take into account only really stabilization by native-like interactions. And so you have a chain which is flopping around, and this is each panel is at 60,000 Monte Carlo steps. And it's only at roughly this stage, rather late in the entire folding process, that you would have what you call a nucleus for the folding being formed. So this is now a structure which gets retained, or at least part of the structure gets retained throughout the folding process from then on. It doesn't dissolve. Okay. Yeah. So you have this, and then you have the native structure being formed. So this is a lattice model simulation. This looks, many people get confused by lattice or cubic lattice simulation. What is, this is obviously not on a cubic lattice, but what this is representing is the average of many simulations. Okay, so the average doesn't have to be present on the lattice points. Okay, the individual guys have to be on the lattice points, but when you take the average, it will obviously not be on the lattice. Okay, so it will be you end up with everything on the lattice, but initially the average gets off the lattice. So they try to identify the transition state by the point where this probability of folding p fold becomes half. So that's roughly at this time t1, and it's difficult to make out in this. So they've actually graded the grayness or the blackness of these squares. This is a measure of the dispersion or the variance in the positions of various residues during the folding time. Okay, so the darker it is, the less the variance in the position of any particular residue in the structure. Okay, so obviously in the native state it's all black because there's no variance, very little variance in the positions of the residues. Early it's mainly white to gray because there's a lot of variance, and you start seeing a transition state where some now residues seem to be getting fixed in position. So residues, for example, here remain fixed in position right throughout subsequent folding. Residues here, for example, form structure, then that structure dissolves and then it forms again, etc. Okay. So the idea is that you have a transition state being present out here because this is the earliest point where p-fold reaches a value of half, and then you have an intermediate, and which then goes on to form the native structure. And this simulation was actually quite interesting at the time it was done in 1999 or so, because until then most of the lattice simulations by nearly everyone were indicating that intermediates were not on pathway objects. They didn't, folding could happen without any intermediate structures. Mainly Peter Wallinis, Jose Hornicek, etc. were all saying that intermediates are traps. Here it was very obvious that the intermediate was directly going to the native structure. Okay. And they did many such simulations. So these are different runs. So these are what they call fluctuation smears for 6 different folding events. So in some cases intermediates would unform, unfold, form again, but finally you would always see an intermediate going to the native state. You would never see an unfolded state going to the native state directly. So it looked like intermediates were necessary for folding to happen. And the other important, I don't know whether you can make this out, we'll ignore this for sake of time. So now they compared 156 independent folding runs at a particular temperature. And so this is the involvement of different residues in the transition state structure. Okay, so this is where p-fold becomes half. There are some residues which are very dark black, which are difficult for me to make out from here. But you can see that for different runs, so these are the transition states of each of those 156 runs, you find that different residues are involved in the transition state. Okay. So this is the type of picture which comes out from simulations of folding. Okay. And there are many, this is a very well-known paper, controversial paper which came out in Nature in 1994 from Martin Karplus and Shaknovich, where they designed a lattice 27 Mer with a native structure, and then they got it to fold and they tried to define how many conformations which form the transition state. And they defined the transition state rather arbitrarily by saying that any conformation which had more than 80% native contacts was part of the transition state ensemble. So this was arbitrary. Ornuchek and company were also somewhat arbitrary. Again, for a 27 Mer, they decided to use Q by Q max equal to 0.6 instead of 0.8. And they saw obviously more members in the transition state ensemble. And they saw that different native contacts had different degrees of participation in the transition state. And they used the word delocalized for the nuclei. And Chan and Dill also, in their work, saw many members in the transition state ensemble. And so they really brought up the point that these are conformations that have to be passed through on the way to the native state because they are responsible for determining the folding rate. So different groups using this parameter Q. Remember, the problem with Q is that it doesn't distinguish between different combinations of native contacts. It will just tell you the total number of native contacts. It doesn't tell you whether you might have 10 native contacts, but those 10 native contacts might be different in one molecule than in another molecule. So we come back to this picture about folding. What then is a nucleus, and how does one get information, at least on a kinetic nucleus? So if you now, as I mentioned, the early studies in folding suggested that folding is at least 3-state or multi-state, that you have folding intermediates. So you go from U to I to N minimally. Then came the idea of 2-state folding, which is folding without observable intermediates. And much of this work by First was on CI2 initially, and then this, many a very large fraction of the experimentalists jumped on the bandwagon and started doing this type of analysis which I'm going to describe. And what they suggested was that folding begins with a tertiary nucleation event. So the history is this, that they discovered a protein which appeared to be two-state. They couldn't rule out a high energy intermediate, but it became very attractive to say that, to kind of discount the possibility of that. Because the moment you discount the possibility of a high energy intermediate, then your transition state is your nucleus, your kinetic nucleus, because everything subsequent to that is downhill. Okay? So the experimental work showed that this structure in the transition state which they identified in kinetic studies was a tertiary nucleation. By that I mean that had both secondary structure and tertiary structure. So short range interactions as well as long range interactions are present in the transition state structure. Okay? And I'll describe how that was done in very shortly. And so this implied that folding began in a non-hierarchic manner. So the idea from this discovery of multi-state folding was that folding happened in step, and the idea again was that proteins look like they've been assembled from you have a secondary structure, then tertiary structure, and then things coming together. So the idea was that the folding process also resembled this assembly of structure. So if you look at a protein, you could easily imagine this helix forming first, this helix forming next, this beta sheet forming next. The idea was that folding proceeded in this hierarchic manner. Whereas this idea of a tertiary nucleation event, especially if it was the initial event, which it would be if it were actually a two-state model, was that folding began in a non-hierarchic manner. That secondary and tertiary interactions, short range and long range interaction formed together. Okay? So the idea of having high energy intermediates was kind of discounted, because then if you had to take this into the picture, then obviously this would not be a nucleus in the sense of it being a state where folding began from. Okay? If you got this structure, this would be a kinetic nucleus and also be the structural nucleus for folding. So they did what First and company developed what is called the phi value analysis. And this is something important because virtually every simulation study will compare the simulation results to phi value analysis. So I'll just very quickly go through this so that you can understand what simulation people are comparing their results to. So the idea is very simple. You all know that you can change these days, or for many decades now, you can change the sequence of a protein at will by mutagenesis. And so that's what is called protein engineering. You can change a particular residue in whichever you want without any trouble. So what you can do is look at your native protein and say, okay, this is an interaction which seems to be important in stabilizing the native state. So you can say, okay, let me perturb this interaction by removing one of the partners. And you can do that quite easily. So for example, you have a salt bridge between a lysine and a glutamate side chain. You can remove the glutamate and put a glutamine, and that salt bridge will no longer form. And you can see how that affects the kinetics of folding. Okay? So the idea is really shown out here. So suppose you had this as your unfolded state, and this is your native structure. Okay? And now let's look at residue position A. If, for example, you do this mutation in the native structure, this engineering the native structure, you would perhaps, because you're perturbing an interaction, destabilize the native structure. So the energy of the mutant is higher than that of the wild type protein. Okay? Now suppose this structure is not present in the transition state. If you're not present in the transition state because it's present in an unstructured part of the transition state, then the energy of the transition state would not be affected at all. Do you follow this? So you'd only affect the native state stability and not the transition state stability. On the other hand, if you mutagenize a position which is present in the structured part of the transition state, then you would not only affect the native state stability, because the structure necessarily must be there in the native state also, but also the transition state energy. And if the structure is fully formed in the transition state, then you might expect that this destabilization here would be equal to this destabilization here. Okay. Now this is where, I've always had a problem, because you're doing essentially thermodynamic studies, getting free energies, and trying to correlate thermodynamics to structure, and that's never, thermodynamics is a science independent of structure, and it's not straightforward to correlate the two, but you can justify by, not just doing one mutation, but by doing multiple mutations in the same segments and showing you get the same type of result. So for example, if this helix was indeed structured, you would not just make one mutation, but you'd make 5 or 6 or 7 mutations and show that you get the same result. Okay, so this is the way. This is what is called 5-value analysis. So you measure kinetics, because from kinetics you can get these free energies of activation and the differences in the free energy of activation. You do thermodynamic measurements to get this change in stability of the native state, and the phi value is nothing but the ratio of this to this, and it's, I think, I thought I'd written some here. Okay, yeah.
Just can you say again what is the problem? You said you have a problem with.
Yeah, so the problem is that you are making a thermodynamic measurement of the difference in free energy. You've mutated a particular residue and you're attributing that entire change in free energy to the structural change which you have done. Okay, it is not straightforward because proteins are quite plastic. If you change a side chain in one part, you might have completely unforeseen results anywhere else. So to make this very direct comparison of you made a very local change, and to say that free energy change which you see for the entire molecule is due to only that local change,
So you don't have a problem making that connection causally, but right? I mean, that is what you've done. But if you attribute the free energy change to only structural change there, then you have a problem. That's what you're saying.
yeah, so
The local mutation can have in effect on a lot of different things. So it's causally responsible,
Sure.
but you shouldn't look just there.
Yeah, there's no way of saying that it's the mutation is having its effect only. The energetic consequences of the mutation are arising only from that local change. Okay?
Consequences are not local.
Yeah. Okay. So I mean, people have been making mutations to proteins for many years, and you see the effect very often felt 20, 30 angstroms away in the protein, and it's very difficult to predict. And so all the good studies where people have done mutations in the 80s and tried to correlate structural changes to thermodynamics, all the good work was really done by Brian Matthews, who not only did the thermodynamics but solved the structure of every single mutant he studied, and there were hundreds of them which he made. So he could really make proper correlations of delta G to structure. Okay. So if this ratio is 1, it means that the altered residue plays an equivalent stabilizing role in the transition state at N, and if it is 0, it means that, because if it is 0, if this is not there, then it plays no role in the transition state. Okay. So the idea was that you would have 5 values of either 0 or 1. Okay. Now what happened was, when many proteins were studied, was that very few, you didn't even see a bimodal distribution. You didn't see many values of 0 and many values of 1. You saw this type of distribution for many different proteins. Most 5 values were partial. Okay. So 0.3, 0.4 were very common. And what does this mean? One explanation could be that there are multiple pathways, and the properties of the transition states on the 2 pathways are completely different, so you have flux along two pathways and you're seeing some average phi value. Or what first obviously suggested was that the interactions were partially formed, that the transition state was a loop. If you had a phi value of 0.5, interaction is half formed, whatever that means. Okay, so that was the general idea of doing phi value measurements. So these are again things which I won't really go through because I don't really have the time. With those of you who want to talk and look at the references in this, it really talks about whether phi values, fractional phi values mean what people think they mean. So what first saw from when he did the first phi value measurements to get, so the idea was then if you had a phi value which is high, then that indicates that for a particular residue position, it means that residue position is involved in structure in the transition state. Okay, and what he found was that there was no very local structure in the transition state, because if you just looked at the phi values which were high, they were diffusively present in the structure of the protein. They're not concentrated in one part. So he then propounded what he called a nucleation condensation model, that you have a weak local nucleus that is stabilized by long-range interactions to give a large extended nucleus. The nucleus consolidates as structure forms, and the consolidation of nucleus and extended structure is concurrent. And whereas in the classical nucleation picture, you had a strong localized nucleus, and the structure grows from this. So growth follows nucleation. So this is what is called the nucleation condensation model, and it's been made popular by First and his group, and a lot of fill-up to this type of thinking came up from studies where, over the years there have been many studies trying to find some correlation to find out what folding rates are dependent on. Are they dependent on stability or on some other feature of the native protein? And one of the factors, a very important factor which folding rates are dependent on, is what is called the contact order. So the contact order is nothing but the local residue separation between pairs of residues in the protein. So a low contact order protein has got mainly local structure, whereas a high contact order protein has got many long range interactions. And you can mathematically define contact order, as I'll show in a minute. But what was found was that if you take the log of the rate constant versus contact order, you found essentially a very nice linear dependence of the log of the rate constant of folding on the contact order. And contact order is a property of the native state of the protein. Okay? And what First then did was to, I won't really talk about this, but he talked about how this was in agreement with his nucleation condensation model, and he brought into so the idea in the nucleation condensation model was that different parts of the chain were coming together. You didn't have a local nucleus, but long range interactions were present. You had these loops which were coming out, flexible loops. You could calculate what the loop entropy was, and you could show that you could change the contact order by making these loops longer or shorter by doing protein engineering. You could just put in residues in these loops if you wanted, and showed that the folding rate increased with contact order, which was increased by making loops longer. So I won't really go into that because I don't really have much time, but it was obvious by this time that the nucleation condensation model of First did not really pertain to the initial event in folding. So then comes the idea is what, in terms of what happens first in the folding, is again a problem which kinetically becomes very difficult to determine, because as I said, that if you have, for example, an intermediate with a helix formed out here, to distinguish from kinetics this type of reaction coordinate diagram from a nucleation condensation type of energy diagram becomes very, very difficult. But the idea is that these are really extremes of two different scenarios. So here you have the phi value of the helix becoming nearly 1 before structure forms in the framework model where you have local secondary structures being formed. Because the idea was if local structures are formed here, by the time they reach this transition state, they should be fully formed. So your phi value for the helix should be 1. Whereas for the nucleation condensation model, you need quite a bit of folding before the transition state is formed. So these pictures are still under debate. There's a lot of question of whether what the nucleation condensation model really means now, how general it is. So if you look at work done with different proteins, so this is a set of 9 proteins. The red guys identify residues which have got a high phi value. So they are native, these are presumably forming native-like structure in the transition state. So you can see that different proteins have different numbers of residues involved in the transition state. Different proteins have different numbers of transition state residues which are present in secondary structures. If you look at the analysis of the numbers of those which are present in the whole molecule, in the helices and the loops, you find that overall higher phi values are found in helices and sheets than in loops and turns. And the idea was that secondary structure has developed to quite a bit extent in the transition state, and so has tertiary structure contents.
Is that obvious or not obvious that you do have
High phi values for
so
the idea
helices
is,
and
so you
beta
need
sheets.
so the idea here is that you don't have I mean the idea initially about this model was that folding was not hierarchic. To have secondary structure being formed, you had to have tertiary long range interactions. Okay, so this is consistent with that type of picture. So you find that overall the average phi value in secondary structure is 0.36 and here it's 0.35 for long range interaction. Okay, so that means that both are present. But what is important now to realize is that this nucleus, this extended nucleus which is coming out from this nucleation condensation model isn't really a nucleus from which folding proceeds formed right in the beginning. It's formed more or less towards the end of the folding process. If you look at other measurements of where along the reaction coordinate this transition state is, it's very near the native state. Okay? So it's not forming, early. It's forming this position in terms of reaction coordinate. So if your reaction coordinate was number of native-like contacts, it would be at a high value of Q. That is why in the simulations, people were trying to identify the transition state by using Q by Q max of 0.8, because experimental studies had indicated the transition state should be native-like. So it tells you after which point folding becomes downhill. That's the utility of this type of extended nucleus. So the idea then is that you may have this collapse or funneling or whatever, and then you have late in the folding process this type of extended nucleus in which many residues well separated in sequence space come together. Now, so what you can also do to proteins when you do protein engineering, protein has an N-terminus end and a C-terminus end, the two ends. What you can do artificially is make circular permutants of this protein. Okay, so for many proteins, the two ends come together in the final native structure. So what you can do is connect the two ends up at the gene level and create a new NNC terminus. And this has been done for many different proteins. So you can make a new end and new beginning wherever you want in the protein. Now, the secondary structure, the sequence, everything in the protein remains exactly the same. the structure of the protein is not changed usually by changing the ends of the protein, of the chain. So that's what's called circular permutation. Now, you would expect that something with exactly the same sequence, exactly the same structure, would have the same nucleus in this extended nucleus definition of a nucleus. But you find that the transition state structures, by doing this 5-value analysis, is different in different circular permutants of the protein. And this has been done for many different proteins now. What? Native structure remains the same. You can see out here. Okay, so but the residues involved in this extended nucleus are changing. So there's some malleability in this diffuse nucleus, extended nucleus, which is so the whole utility of such an extended nucleus in terms of understanding the folding process is, to me, a matter of contention. Okay? So you have an extended nucleus, for example, here. This is a protein which has been studied more recently. It folds extremely fast. Its structure has got virtually all the elements in the final native state. This extended nucleus in this folding of this protein. So I'll quickly talk about some other type of work, not protein engineering work, but work in which you look at proteins whose structures are known. And so this work has been done by Peterson and several other groups. And what you can do is this: if you have a family of proteins which has got many different members whose structures are known. So for example, if you look at the C-type cytochromes, so these are very important in your energy production in your cells. There are thousands of these sequences which are known. This was work done in the late 90s. Similarly, there are lots of globins. Globins are the hemoglobin and myoglobin. There are large families of proteins and many sequences are known. So the idea was this: you look for residues which are conserved in evolution, but which are not involved in the function of the protein. Okay? You look for non-functional conserved residue positions. And the idea is that these positions not important in function are important instead in folding. Okay? And you then try and see, are these conserved non-functional residues coming together in the structure of the protein? If so, do they play the role of a nucleus in folding? Okay? So they looked at clusters which they could identify clusters in both these groups, large families of proteins, and they could, these are proteins also, cytochrome C and myoglobin are workhorse proteins for experimentalists. So a lot is known about their early folding intermediates, equilibrium intermediates of the protein, and they could show that these clusters which they identified by just doing sequence analysis were also present in the kinetic intermediate and equilibrium intermediates, and they seem to be tightly packed in the intermediate as in the native state, in what was called an equilibrium molten globule intermediate. Okay? So they make the remark that folding intermediates are usual but not obligatory features of folding, because by the late 90s, the work of Wallinis and Onuchik had caught on, and everybody had started talking about intermediates not being directly productive to the native state, even though the simulation I showed of Vijay Pandey showed intermediates being necessary for folding to happen. So the idea was that these clusters may represent folding nuclei common for all subfamilies of the given family. And so, for example, in cytochrome C, they looked for, they've identified this cluster of residues which was conserved throughout the family. These were not involved in function, and this was what they thought might act as a folding nucleus, but I don't think there's been any experimental work to see whether it's actually a folding nucleus. So the idea of experimental work to verify whether it's a nucleus is the idea is this, that if it's there in the transition state, then if you change these residues, then you should affect the kinetics of folding drastically. Because if this interaction is present and is stabilizing the transition state, if you remove one of these residues and then put something which will not perform this interaction, then you should destabilize the transition state and folding rates should change drastically. And that's indeed what is seen when people mutated residues which show high phi values. And similarly in myoglobin, a cluster of residues could be 6 residues could be identified. So I'll kind of stop right now. This is just another paper. I mentioned a result of Shaknovich from his simulation work, which seemed to indicate that residues identified as nuclei by phi value analysis were conserved in evolution. What they did was a more thorough analysis of many different proteins where phi value analysis had been done and showed that this was not really the case. So that what was identified as nuclei by simulation were not really conserved in evolution. So I think I'll stop there, and if there are any more questions, I'll be happy to take them.
I said a summary may have been useful because I think there are many twists and turns in the story. So
Okay.
maybe that's the first thing that I would like to ask. So in terms of, so the last bit was inconclusive. So this is a continuing story, I suppose. So, but
no, so you can, I think, identify residues which are forming, presumably, if you believe in this phi value analysis, residues which are involved in what you might call a kinetic nucleus, in the sense that after that, folding is very rapid and downhill. So that you can do, but to identify which are the structures which are formed first during folding, that becomes a big, that is still very difficult. So,
but in terms of conservation during the evolutionary history of these proteins, this is inconclusive.
well, it's not, it's inconclusive, yeah. It's not conclusive.
Could you please keep the last transparency on show here? The last one, the view we are seeing.
It's kind of related to what Shrikant just asked, which is that if you looked at all proteins for which you have data on these residues that make up the nucleus, what is the sort of generalization that you can make, not just in a given members of a given family, but across the whole data set of proteins? What is conserved? You say the number of residues was not conserved. The specific residues themselves were not conserved.
I mean, if you look at cross families of proteins, there's nothing conserved in terms of what might be a structure in the transition state. So as I
Good afternoon. We start this afternoon's program now. Like yesterday, the two talks this afternoon will be on protein folding and aggregation. Well, I should say like it was announced for yesterday, because Dave did sort of change part of his talk, talked about RNA experiments. But okay, so the first talk will be nucleation in protein folding. And Jayant, after the break, will talk to us about mechanisms of amyloid fibril formation. Jayant.
So I understand that nearly all of you are physicists, and both talks today are really talks which describe the approach a chemist would take to study both folding and protein aggregation. And so I will allude to some computational work done by physicists. I will allude to some physical models, but the idea really is to present the other viewpoint to most of you, the viewpoint of those who do experiments on protein folding and protein aggregation, and what they think about processes happening to proteins as they either fold or undergo the other type of self-assembly, which is into aggregates. And I'll be talking about how they go into regular aggregates called amyloid fibrils. So before I start, I should warn you that I have some slides which are handwritten, and if you're right at the back of the room, you won't be able to read them. So unless you want to sleep throughout the talk, you might want to move in front. The first talk has only a few handwritten slides, but the second one has probably a dozen slides which are handwritten. So I'm going to be talking about nucleation in folding. And before I really start, I presume from Dave's talk yesterday and also talks in the previous week that you all by now know roughly that proteins are heteropolymers, that the polymeric chain is really a necklace of beads of 20 different colors, and each bead of each color is got a different type of chemistry. So some are nonpolar, some are charged positively, some are charged negatively, some are polar but don't really have a charge. And because of this, because proteins are heteropolymers, they have a chemistry of interaction which is very important in dictating how the structure is arrived at. And physical models of folding usually ignore the chemistry. The well-known funnel models, for example, really give no importance whatsoever to chemistry, and they ignore, they will only consider the protein as a chain whose energy barrier to folding arises completely from chain entropy and not from interactions within the chain which might be difficult to form. So if we now talk about a process such as this, which is going from a necklace of 20 different beads to a well-defined structure. So this is what you would call the unfolded state, and this is the folded state. Now, we know a lot about this state from crystallographic studies. There are tens of thousands of proteins whose structures are known right now. We know structures from NMR studies. Those are not perhaps as precise as crystal structures, but nevertheless there are still several thousand NMR structures available. Unfortunately, we know very little about the unfolded state. The unfolded state has been called liquid-like. What that means is something which really reflects the point or the fact that one knows really very little about its structure. So it's been called liquid-like. There are lots of interactions present within the unfolded chain which are present in the folded chain. So you would have, except that the partners would be different. So you all probably know that proteins are stabilized by van der Waals interactions, hydrophobic interactions, electrostatic, hydrogen bonding, etc. Interactions between aromatic side chains, etc. And many of those interactions could be expected to be present out here. And it's very difficult to get structural information on the unfolded state because the methods of doing so are rather difficult to utilize. One can nowadays by NMR get some information about local structures in the unfolded state, but the experiments are pretty tedious to do and not very straightforward. And it's important to get some structural information on this because if you, for example, know that there is some element of local fluctuating structure in the unfolded state, perhaps that structure might play a role in seeding the folding process. So it's become very important to look at the unfolded state. Now if you look at the unfolded state, and now when we talk about unfolded state, I presume by now that many of you would be knowing that you unfold a protein by taking it into a high urea or high guanidine solution, or you take it to a high pH or to a high temperature. So if you unfold the protein chain, if you look at the distance distributions between points on the chain, especially for example if you look at the radius of gyration, or you look at end-to-end distances, these distances have distributions which are expected for a statistical random coil. So you would expect really there to be no specific structure in the unfolded state. But it's been shown by several groups that even if there are elements of structure in the unfolded chain, the distance distributions would perhaps still follow a Gaussian distribution characteristic of a statistical random coil. So it's not easy just by showing that you have a random coil distribution to say that there is no structure. You need to do the hard experiments to see whether there is structure, and typically you would do those experiments by NMR, and I will allude to one such study in the course of my talk. Now, so we want to know now, yes?
What kind of structures, if they're present, will also give a Gaussian distribution?
So what you can do, for example, and what has been done by George Rose's group, is just you take these elements of secondary structure, the helices and the strands, and in between out here, or even somewhere, even in the middle of these, if you now just randomize the phi psi angles, so you would essentially get small units of structure but otherwise randomized in arrangement with respect to each other, and then you look at, for example, the radius of gyration, you would still see a distribution, a Gaussian distribution. So it's not